Good morning, mathematicians. Yesterday I said I'd keep it short, and it didn't end up being that short. Today I think it will really be short. But again, I say that. Will it be? I wanna do some writing, and I gotta go hit leg day, of course. But again, I say that. Will it be? But before that, D modules. Probably. Yeah, I guess that's what we'll talk about. So I think last time we were talking about computing the minimal extension of some D modules, or at least determining it axiomatically. So let's get back to doing that. Right. So we were looking at this D module. Was it dx.del? Yeah. Whose global sections, I should say DC, I guess, whose global sections are given by this. And we verified the first property, but we wanted to check that there was no non-zero modules supported on, no non-zero D modules supported on zero. Yeah, so, but I realized, what did I realize? Actually, I thought I had a thought about this after stream yesterday. Right. Well, suppose that we had, so basically it'll correspond to some ideal, right? Because it has to be a sub OX module of this thing. So, well, I mean, okay, it doesn't even matter so much that it's an ideal, but just suppose that we had some non-zero F, and I guess, really, if I'm being careful with my notation, I guess I should suppose this is some F over some section, some open set. Well, then notice that, actually, wait a second. I got confused about this because the support on that, is that just the stock? I guess that's just the stock. Right. So anyways, the point is, though, that if F is in there, then certainly whatever submodule we're considering, so suppose there's some submodule M of some D module, sub D module M in here, and let's say F is in M, then that means that del F is in M. But in this case, del F just acts on F as the ordinary derivative. And so, basically, by successively applying del, that means that, well, the constant, or the leading coefficient of F has to belong in M, because basically you just keep applying it until you end up getting, well, you get a non-zero scalar, basically. But then once you have a non-zero scalar, you have 1 in here. And well, I claim that this generates the entire module, right? Because in this case, it's basically like, yeah, I mean, again, this module is generated by OX and the differentials. I mean, the differentials are basically killed, so the actual symbols themselves don't appear, but they can still act on these F and take derivatives. So basically, well, as soon as you have 1 in there, then you also have X acting on 1, which just acts by multiplication, and that generates like all of the global sections. Hello, Duck with a monocle. Good morning. I see chat is kind of cut off, though. I don't... Yeah. There we go. So, yeah. So, in other words, never mind no non-zero modules supported on the parts of the closure other than the set itself. But in fact, there's just simply no non-trivial sub D modules. So we know that we have a simple D module. Wait a second. Now I'm very confused because I thought these... Good morning, Lola. I'm very confused because I thought these minimal extensions were always simple D modules. But maybe... I see. Okay, here's what I think is going on. The minimal extension can actually be applied to any D module, so it's not necessarily simple. So you do need condition 2 in general. However, I believe it is the case that if we follow the recipe I was talking about before, where you start with an irreducible local system, and you bump this up to a corresponding D module, and then you take minimal extension. If you started with this thing being irreducible, then I believe number 2 comes for free because your module is automatically simple. Yeah. Sorry, did I say hi, Lola, yet? I saw you said hi, and I literally just blanked. I gotta have more coffee. Okay, so now we need to write down... Did I start writing? I thought I wrote down the transfer D module. Oh, I did. Yeah. Okay, so we need all of this. I did say hi. Okay, I'm losing my goddamn mind. Okay, so now here comes the hard part, because we have to compute some derived functor nonsense, and we're going to have to do some derived pullback. Well, actually, I think we could rely on another theorem here. If I ever do another rating your proofs thesis video, I should definitely cosplay as Men in Black agent with a neuralizer. Nice. That's actually a very good... that's actually a really great thumbnail. Necessary but not sufficient. Yes, indeed, Boris. Yes, indeed. Yeah, Duck with the monocle. I should remember that. Funny story about Men in Black. The original Men in Black, the first one. I I don't remember what it was, but I did something when I was a kid. I got in trouble for something. And so as a punishment, my mom took away my Men in Black VHS tape. and but then they hid it so well that my parents lost. They didn't know where they had hid the tape. So then later they ended up buying me a second Men in Black VHS, and then of course later, the first one was found, and so that's how I had two copies of Men in Black on VHS. So I feel like accidentally, I have a lot of stories in which my parents accidentally reinforced bad behavior. So like the long-term takeaway was like, oh, if I misbehave, I will get two Men in Black VHS. Okay, write that down. Dark Knight, we're discussing more demodule nonsense. More demodule nonsense. Yeah. And I'm going to try to appeal to a theorem here to make my life easier. Although really one day I would like to, one day I'm going to need to not do this for an open or closed orbit. And then I guess life just gets harder for me. Yeah. So let's see. Actually, no, there is a trick to even make life easy in that case. But let's see. So we're in the case of an open embedding. Because we're talking about the... we want to see what happens when we restrict back down to the open orbit. For open embeddings, irreducible affine varieties. Yeah, I think that's true. They are. So the pullback just becomes the usual restriction. Okay. And the usual restriction is exact. So I guess all the derived phenomenon disappears and we get lucky. I think that's the case. I think that's what this is saying. So, right. So let's think about our D module. So, what is our D module then? If we were to restrict back down to the open orbit, well, this is basically just generated by OX restricted to the open orbit, and also our sheaf of differentials restricted to the open orbit. But again, because we're taking this quotient, actually the derivatives pretty much all just disappear, and we're left with really O of C star, right? And at least as the underlying quasi-coherent sheaf. And if you remember, we did do the calculation where we talked about having O of C star as a D module, or rather, sorry, as a as a D module. And how was that D module defined? Well, we said that we would take the exterior derivative, take that pair, and then give this the structure of a D module, where of course O C star just acts on itself in the ordinary way. And then we use our formula of how to go from a connection to a D module to see how derivation should act. And we said it would be exactly in this way. So let's see. That's what we get. I mean, that is definitely what we get in this case. So dx, right, what am I saying? Okay, so we already know it's going to be this restriction, right? So the underlying sheaf is this one. Awesome, we're on the right track. And how does and we already know that this acts in itself from the natural way. That's just coming from the D module that we started with. So really, the only thing we have left to check is that this action here works out to be the one that we think it does. So in particular, if del is acting on this module from the left, it's just taking derivatives of whatever functions are there. And sure enough, well, how's this connection defined? It's defined with the exterior derivative. And we said that was going to be the one that took this to df tensor 1 plus, well, that was just it. That was just it, right? And then evaluate at del. Hello, CS student here, looking into Gaussian processes. But you're a big fan of math in general. Great. Well, you come to the right place. This is a channel about math in general. Although the last couple of weeks, my live streams have mostly, aside from some viewer questions, mostly I've just been talking about the subject of D modules. But nice to have you here. Now the exterior derivative of f, that's just the partial derivative of f with respect to x times dx tensor 1 evaluated at del. But remember, we said that that's just going to be the derivative of f with respect to x at dx evaluated at del. But dx evaluated at del is 1. And so we find that the derivative of f, this is the derivative of f with respect to x, which is exactly what we expected. Yeah, D modules are kind of complicated things, to be honest, Victoriano. But if you do, all my live streams are saved. So if the last, there was a break, and then I started live streaming again, maybe like a week ago, and I started D modules from there. Although, so there's some explanation there, but I should warn you that I didn't necessarily start from ground zero. I didn't necessarily start as a D modules for total beginners course. But maybe those videos will be helpful. I have no idea how much algebraic geometry background you have, though. So it may not be helpful at all. Okay, so that actually completes the verification. That actually completes the verification of the minimal extension of... so we now know if we take... the minimal extension, then applied to this D module, then we recover the D module that I said it would be. Yay! Great. Computations. Why I care about D modules? That's a good question. Because, I know why I care about D modules, but in the grand scheme of things, it's kind of a niche sort of topic. Well, I don't know. Kashiwara just won the Abel Prize this year. I think not unrelated to his work on D-modules. So to be honest, I don't know how D-modules fit into the world of... I don't know how D-modules fit into the broader scheme of things, or how they're used in different, or, in terms of differential equations. Like, I don't know the big impact they've had there, necessarily, which I imagine is a bunch. You're reading, it goes into ring theory and manifolds. That's true. Those are definitely essential ingredients. And both are hot topics at the moment in machine learning. I didn't know that ring theory was a hot topic in machine learning, but I guess I could believe that. Yeah. Get a base grasp on them. Yeah. Well, there's definitely there's a lot of resources out there. I'm sure that nowadays there's a lot of books or articles or whatever geared specifically to machine learning people, because these are both, manifolds and ring theory are both very deep and vast fields, about which there are many resources, fantastic resources, but also many that would be, orthogonal to the most direct applications. But, well, yes, because D-modules are fun. That's right, Lola. But maybe to answer my very niche perspective on where D-modules come up, and I don't know. I mean, again, it's hard to answer this question if I don't know your background, because I'm going to justify this in terms of other things, but then you could just as well turn around and say, well, why are those other things interesting? So one would like to understand representations of groups, namely complex Lie groups, and those can be captured in terms of modules over its Lie algebra, its complex Lie algebra. And so there are questions. The topic of my thesis is about the p-adic version of the Kasdan-Lustig hypothesis. Which I'm not going to mention that version, although that's exactly why I care about D-modules, but maybe the sort of more classical explanation is, well, we want to understand, there's some questions we want to understand about representations of complex Lie groups. We go over to Lie algebras, kick the can down the road a bit, because that linearizes everything. This turns things into linear algebra. Presumably those questions become easier to answer. Well, we still don't quite make progress there, but we take, so we transform the problem again to look at modules over what's called the universal enveloping algebra. Again, the problems don't seem to reveal themselves, so we try and transform the representations. Again, it turns out, though, that modules, so the universal enveloping algebra can be interpreted as a special kind of differential operators on your manifold. So that is where the connection to D-modules comes in, because those are like families of, differential operators. And so it turns out that this is equivalent to looking at D-modules on a special quotient of your group by a special subgroup, and in fact looking at the equivariant one. So I think the group is maybe you take there's some other group involved here, something like this. And so the sort of crucial Kasdan-Lustig hypothesis, which is a guess about counting certain kinds of representations for this group G, you push it down over to D-modules, you do one final correspondence. This is called the Riemann-Hilbert correspondence, which I'll talk about, where you finally get down to equivariant perverse sheaves on here. Okay, and now I've said even more fancy word. But then, if you do this, and you prove that some fancy cohomology stuff, And it seems like we've taken a hard problem and just made it harder. But at the very end of the day, you then prove a theorem that fancy cohomology stuff can actually be computed entirely in terms of combinatorics. And now, at the end of this big, long theoretical process, you can solve important problems about Lie groups using your computer and have it just compute the answer for you. So that is a very rough explanation of why I would care about D modules, is because they're a critical step in interpolating between these two things. Actually, this is not entirely accurate. Like I said, this is the classical reason. I know a classical reason of why D modules were so important. But oh, someone's ringing my doorbell. Hang on a second. Okay. Anyways, so what am I? Is the fancy cohomology stuff the titular K theory or no? No. So the K theory is actually I don't really work in K theory. Is this K theory just because my name starts with a K and I thought it would be a good channel name. But actually, so, okay, I said no, at least in this perspective. However, the case that I actually care about is for, instead of these varieties, there's these varieties that come up, in the local Langlands correspondence. And so really I care about like equivariant D modules / perverse sheaves on this other variety. And the proof or proofs of various parts and versions of the Kasdan-Lustig hypothesis here does actually involve K theory. At least, so there's a special cases of this Kasdan-Lustig hypothesis that focus on, so namely like the work of Chris and Ginsberg, where the way that they establish these results, they actually don't talk about D modules, they just talk about the perverse sheaf perspective, but of course by Riemann Hilbert these are equivalent. And they sort of use an approach where they pass through some sort of like equivariant Riemann Roch type theorem, and they do actually use some like they deal with this like variety and this group acting on it, and they deal with like this equivariant K theory ring, and then they have some comparison map from cohomology or like equivariant cohomology or something to this K theory ring. So somewhere lurking in the background, actually, it does pop up, but I don't know much about that. Yeah, maybe ring theory is not a hot topic, but you read it as very useful for advanced linear algebra at one point, and linear algebra is useful in ML. Yes, although I don't think you actually need like the advanced ring theory version of linear algebra. It's just like it turns out, linear algebra, normally you're dealing with fields, and of course as a mathematician you want to say, well, how far can we push this? Does it only apply to fields, right? And so it turns out you can push a lot of linear algebra much further than fields, but I don't think any of that is necessary for machine learning. I think for machine learning purposes, you're totally happy just with the field version, and probably just particularly the real numbers and or finite fields. That would be my guess anyways. I don't really know a ton about machine learning. You're a grad student who took up Calc 3 and linear algebra, and now this year looking into advanced grad level math on Bayesian statistics for Gaussian processes for your background. That makes sense. That makes sense. Yeah. Is taking a combinatorics course recommended for a pure math student? If you... Well, I don't know. If you're interested in combinatorics, then yes. I mean, I guess you should take one anyways, right? To be a well-rounded mathematician. You'll probably have to count something at some point. Like, I feel like there's people... So I have a bit of a combinatorics background just because I did my undergrad at a very combinatorics-heavy university. And there's people in my research group who just, like, hate combinatorics. And they're like, I can't do these calculations. I don't like thinking about them. And then, so, I do them. And so then that, makes me slightly more useful. Because I can take on that role in the group. So, it could be useful. Well, it depends. I mean, you could also, if you wanted to make a career as in combinatorics in pure math, well then, yeah, you should take as many combinatorics courses as possible. But you could also probably live a happy life as a mathematician, ignoring it forever. I think it's better to just, get a lot of breadth, but... I think you might be mistaken there. Unfortunately, yeah. Combinatorics, not clear to me that they would be related to hypergeometric distributions. Okay. All math is related to all other math. I'm sure one could find a place where combinatorics interacts with hypergeometric distributions, but... the latter seems quite analytic in nature, which can be very different from combinatorics. Of course, combinatorics does intersect with analysis in interesting ways, but when I hear those two terms, I'm not. It doesn't strike me as two fields that are intimately related to each other. Okay, but I'm gonna keep honest to what I said, that I'm keeping the stream short today. So I'm gonna end it there. I'll see y'all very soon. Like tomorrow probably. You don't like combinatorics, but you want to do algebraic geometry, and you've seen a lot of it in tropical geometry. That's why you're thinking about it, yeah. Well, if you don't like combinatorics, then, well, I don't know. There's two trains of thought. One, try and make yourself like combinatorics, or two, just steer away from it. So yeah, algebraic geometry is a vast field. So if you've seen a lot of it in tropical geometry and you don't like combinatorics, then just steer away from tropical geometry. Don't do that kind of algebraic geometry. Yeah, I don't think in this case there's a direct relationship. Although I'm sure there is maybe some relationship out there. But yes, I would say combinatorics is generally useful. It's probably more directly applied than my research, I would say. Machine learning grad students do need some algebra beyond linear algebra. Vaguely recall your friend talking about something symplectic. Oh, that's interesting. I could believe that. I could definitely believe that. Well, maybe I will browse some machine learning material sometime soon, because it could get me a job in the future. And if there's something symplectic going on, then I'm interested. Anyways, okay, I'm leaving for real now. I'm gonna go prove some theorems. You better go prove some theorems.